Hello and welcome to Lecture 10, Part 1, where we're going to continue talking about linear oscillations. And we will begin with a brief recap of what we did last time. So last time, what we did, we started with a system with some complicated dependence of potential on space. And we let a particle of energy E. And our goal was to try and figure out what would be the linear description of oscillations that a particle of this energy would have around the minimum of this potential, around the equilibrium point, around the x equilibrium or the x naught as we decided to denote it. So what do we do in order to approximate the motion of the particle in a complicated potential? We try to replace it with a potential that allows us to solve for motion near the equilibrium point in the easiest way, and at the same time approximates that motion really well. So what we did, we approximated the behavior of this function near the point of equilibrium with a parabola that had approximately the same shape as the potential itself near x naught. And so what we've done is we basically have replaced the potential V with a parabola. And why is this called a linearization? Well, that's because V that scales as x squared as a parabola results in a force which is given by minus dv dx. That scales as x to the first power. So the force is linear. This is why we refer to this as linearization. And so the idea here, in this case, is to take a nonlinear system and try to make it look like a bunch of linear oscillators. So what was the way that we considered this linearization? Well, we replaced v of x with its harmonic approximation and wrote down the Lagrangian, which is t minus v, in the following form. And now we can do the same for multiple particles. So how does it look like? It looks very analogous, but now we're switching to the matrix form. So the kinetic energy will look like this. And for potential energy, we will write this through the V matrix. How did we go about solving this system in the old way? Well, we wrote down the Euler-Lagrange equations, which gave us m double dot equal to minus m eta double dot equal to minus k eta. Then we solved it by the substitution. So it's an oscillatory sinusoidal solution, periodic solution. And by plugging this here, we were getting eta double dot gave us two factors of minus I omega, so minus I omega squared. I squared gives us a minus sign. Omega squared gives us omega squared times m. K eta just gives us the k factor, and all of this is multiplied by a and gives us 0. Note that we're interested in non-trivial solution, so that a is non-zero. So how do we solve for this eigenvalue problem? Well, clearly if a is non-zero, then the prefactor minus omega squared m plus k has to be 0. So this is precisely what we demand, that this prefactor is going to be 0, and as a result of here, we're going to get that omega squared, the eigenfrequency of the system, is square root of k over m, or omega squared is k over m. So we can take a fully analogous approach for a system of many particles that are described by the matrix approach. So we can write down the solution here as eta, a vector that is a vector of amplitudes times minus I omega t. And if we plug this into here, then we're going to get 2 factors of omega from here, right? Each eta dot gives us an omega, and no factors of omega from there. So what we're going to get is something that looks totally analogous to what we got before, except m will be replaced with tij. So we're going to get minus omega squared times the T matrix plus the V matrix, and all of that will be multiplied by the vector A equal to 0, where of course A is not equal to 0. We're interested in non-trivial solution. We're interested in the amplitude associated with the eigenmodes, with the eigenvectors. So in full analogy to the scalar case, in the vector case, in the case of multiple particles, we need to demand that for A to be non-zero, there has to be an analog of a statement that this expression in parentheses is 0. And in the case of matrices, in order for that to be true, we need to demand that the determinant of this matrix vanishes. And this is going to be the condition that allows us to determine the eigenvalues or the eigenfrequencies of the system. So this is the eigenvalue problem. And typically when we write it out, we're going to get an equation for omega squared, and this will allow us to find what omega squared is, the eigen frequencies. So we're getting some sort of equation for omega squared. Great, so this is a recap: the scalar way for a single particle and the vector way for multiple particles. And we're going to follow through on this and try and see how to work with these multiple particles and multiple eigenvectors and eigenvalues, and how to make sense of these more complicated systems. So stay tuned, and I'm going to see you after you're done with the quiz. See you, bye-bye. Hello and welcome to part 2 of lecture 10. What we're going to be talking about now is more linear oscillations. Namely, we're going to be talking about coupled oscillations. So what does it mean? Well, it means that we have several oscillations happening at the same time. We have multiple generalized coordinates, all of which are oscillating around their respective equilibria. And we're using matrix approach to represent the state of the system. So how does the matrix approach look like? Well, let us copy it from right here. We will have a matrix T, which represents our kinetic energy, times the double dot of our displacement from the equilibrium, that's the displacement vector, plus the contribution from the potential to our system, multiplied by the displacement. All of that is going to be equal to 0. If we take an oscillatory guess solution and plug it in here, then we're going to reduce this to a matrix equation like that, which is basically another way of writing down an eigenvalue problem. And in fact, we can write it out in this following way. V times A is equal to lambda times T times A. That is an eigenvalue problem. And I would say this is a new eigenvalue problem because the regular eigenvalue problem doesn't have a T over here. So that's why it's a new eigenvalue problem. And lambda here is going to be equal to omega squared. That is an eigenvalue of this problem. So we replaced omega squared with lambda just to make it look more like the regular eigenvalue problem. Before we move on, let me introduce a few new things about the notation. So we will be dealing with vectors. We're going to have to decide what symbol we use to denote transposition, complex conjugate, and transposition plus complex conjugate. So we will transpose a vector by denoting it with the upper index t, or to comply with Goldstein, we will denote transposition via a tilde above the vector or a matrix. We will denote complex conjugate via a star, so that would be complex conjugate. And finally, we will denote a composition of both of these, rather a combination of both of these, transposition plus complex conjugate via cross. So this will be a tilde plus a star. So that is our notation that we're going to be using from here onwards. And this is also the notation that Goldstein uses, the tilde and the cross and the star. So let us now pose a theorem, and then let's try and prove it. If V and T are symmetric and real matrices, and T is positive definite, then the eigenvectors and eigenvalues are real. And in our future notation, what it will mean is that the matrix made up of eigenvectors and the eigenvalues themselves are going to be real. B is that different eigenvectors are orthogonal to each other in a special way. Namely, what that means is that a tilde times T times A is equal to an identity matrix, where A again is the matrix made up of the eigenvectors. And finally, C is that the matrix of eigenvectors diagonalizes V. Or, in the matrix notation, A tilde times V times A is equal to the diagonal matrix with eigenvalues along the diagonal. So that's what we denote here with lambda with 2 underscores. So, how are we going to go about and show that this is the case? Well, let us write down this eigenvalue problem for one of the eigenvectors. Let's say A with an index k. So we're going to get V times AK is equal to lambda k, which is a scalar, so there is no underline over here, times T, a matrix, double underline, times AK. Awesome. So what is the trick that allows us to prove this? Well, let us multiply it on the left with the transpose and complex conjugate of AL vector. So we're going to get in the end AL cross times V times AK is equal to lambda k times AL cross times T times AK. So far so good, right? Well, let us now do a complex conjugate and transpose to this equation. So we're going to get AK cross times V times AL. That is because V is symmetric and real, therefore everything else changes, but V remains intact under this operation. Here lambda k will get a star because it is a scalar, so when you transpose nothing happens to it, but when you complex conjugate apply to it, then it gets complex conjugated, so that hence the star. And then here we'll get the same exact AK will get a cross and we'll change the order. T will stay intact because of the same reason, and we're going to get AL on the right. Great. Now you see that we are getting something. We're getting something similar to the above equation, apart from the fact that we have lambda k and lambda k star. So what we will do, the last permutation here, we will switch k and L. And what we're going to get in the end is AL cross times V times AK is going to be equal to AL star times AL cross times T times AK. So this is really good. What we can now do, we can take these two equations and subtract them from each other. Subtract them from each other, and what is that going to give us? It's going to give us 0, because the left-hand side parts are exactly the same, right? AL cross VAK, AL cross VAK. So we're going to get 0 for the left-hand side. The only difference here for the right-hand side is lambda k gets replaced with lambda L star. So it will be lambda k minus lambda L star. And the rest is exactly the same. So it will be AL cross times T times AK. So there can be two cases over here. Case number one is if K is equal to L. Well, in this case, we're multiplying T by AK from both sides. And because T is positive definite, it means that this part has to be greater than 0 for AK that is non-zero. That means that in this case, if this is non-zero, the only possible way of satisfying this requirement is that lambda k is equal to lambda k, like k star, right? So that means that from here, we conclude that lambda k is real. And that proves this point. Different eigenvalues are real. So that's point A2 that we have just proved. So let's consider the second case in which k is not equal to L. So what will happen in this case? So if k is not equal to L, and because different eigenvalues are different, it means that this product over here has to be 0. So what we're gonna get is that AL cross times T times AK, this has to be 0 in this case. And that means from here that A's are real. Why is that? Well, it's because this is a system of linear equations with real coefficients. Therefore, the solutions, meaning the components of A, are going to have to be real. This means that we have just shown that A1 is true, that eigenvectors are real, which is great. Finally, from here, we also show that the different eigenvectors are orthogonal to each other. Or this is statement B. So this is the statement B. Different eigenvectors are orthogonal to each other in a special way. And this is the way in which they are orthogonal. It's not that you multiply one eigenvector into another, you don't dot them into each other, you dot them with the T matrix. So this is the special way in which the eigenvectors are to be dotted into each other, and this is the special way in which they are going to be orthogonal to each other. And so from here, from these two, we're going to be able to make a conclusion of how different eigenvectors relate to each other, namely AL cross times T times AK is equal to delta LK. So if L is equal to K, then the eigenvector dotted into itself through the T matrix is going to be equal to 1. And if L and K are not equal to each other, then the different eigenvectors are going to give you 0 when you dot them to each other. So it means that they are going to be orthogonal. Okay, so that is really good. What we'll have to show is that the matrix of eigenvectors diagonalizes V. So let us try and see how we can show that. But before we do that, please don't forget to fill the quiz. Hello and welcome to the last part 3 of our lecture 10, where we're going to be talking about the matrix of eigenvectors and what happens to our V matrix. So let us put our eigenvectors together into one single matrix such that every eigenvector is going to fill one column in the matrix. So our eigenvector matrix will be denoted as Aij, and it will have vector A1 followed by eigenvector A2 and so on. So we will have A11, A21, and so on. And here we're going to have A21, A22, and so on. All of this is going to be also denoted as Aij. So what does each of the indices mean? So I here means the row number, and J here means the column number. So this is I and that is J. So here similarly, I means the row number and J means the column number. So, and these are the eigenvectors. So the very first column, column J equals to 1, is our first eigenvector. Column with J equal to 2 is our second eigenvector, and so on and so forth. So how does the orthogonality of eigenvectors look like? Well, with our matrix T, we can write it down as AL cross times T times AK is equal to delta LK, where delta is the Kronecker delta. So another way of writing down will be in components, where we can replace this matrix multiplication with component by component multiplication. So you can see that this multiplication of a row matrix with a T matrix will be done through a contraction between AIL and TIJ, and contraction will be done over I. So here Einstein's summation over repeated indices is implied. And here on the right, the matrix multiplication of the of T matrix times A vector is done through the contraction over the index J. And in the end, we're going to get exactly the same outcome, that the answer is delta LK. This is just another equivalent way of representing exactly the same mathematical statement. So here, I should be, if we were to matrix multiply, this should be the column number, right? Because if this were a matrix that multiplied matrix T, right? So AIL is a matrix of two indices, just like this one, right? Then in order for us to put the two together in a matrix notation, and for the multiplication to behave exactly the same way as we wrote it down here in components, then I should have been a column number, right? Because when you multiply a row times a matrix, it's the row times the first column times the row times the second column. So I should enumerate the elements in the row, and so should be the column number. So similarly, J should be a row number. So how can we then represent these such that these two are correct? Well, in this case, we can represent this by taking the elements, the Lith element of the transposition of this matrix, multiplying that by Tij, and then here we are going to take the matrix itself. It will be Jk. So let us double check. So here we are going to be going along the columns in the very first row for L equals to 1, the very first row. We're going to be going from left to right. I is increasing, and we're going to be dotting that with increasing rows in Tij. So yes, it's working out, and here it's working out analogously. And all of that will be equal to delta Lk. So this is awesome, which means that we can rewrite this using the matrix notation simply as A tilde times T times A, and all of that is going to be equal to the identity matrix, the one that has ones along the diagonal. So this is awesome. Let us now try and do exactly the same thing, but for the V matrix. So how would that work? Well, in a very similar way, AL cross times V times AK is equal to lambda K times AL cross times T times AK. So we can then rewrite this in the matrix form in full analogy with what we've done here by writing that A tilde times V times A, and we're going to take the Lk element of that is going to be equal to lambda K times the element of the identity matrix, which is A L cross T AK, we've shown to be equal to the identity matrix. So here we can rewrite this per component statement in a matrix form by introducing the matrix of eigenvalues, which are sitting along the diagonal. So all of these are zeros, as lambda with 2 underscores. So this will be a matrix of eigenvalues which are written out one by one along the diagonal. And so now we can summarize what we have learned. We've learned that the matrix of eigenvectors and the eigenvalues are real. We've also learned that the eigenvectors are orthogonal in a special way, and that the matrix of eigenvectors diagonalizes the matrix V. This is it for this lecture. Next time we're going to take a look at a few examples, and we also are going to look at normal oscillations. Thank you. Bye-bye.